the presentation for 15 minutes. So let's see how it goes. Thank you. Well, I'm here to explain the continuation of the work that has been done. I mean, the next stage downstream for the generation of these VFAs to give a global perspective and to look at the future potential of the application of these VFAs. And first of all, I'd like to mention and explain, is actual clicker not working? It does not seem to work. Well, you know, technology. Well, let me tell you what Repsol is doing in this kind of session. I don't think we need to explain our context. We are a company well known for being an oil company. We are currently an energy company globally. And in the current context, in the current framework, we are undergoing an industrial transition towards circular economy and sustainability, trying to include new raw materials to replace crude oil and oil. So currently, as you may know, our CEO was the first CEO to announce in our sector full decarbonization, that is reaching net zero emissions by 2050. So we have set out a decarbonization roadmap, which is quite challenging and complex in our sector. But we are taking the right steps, in my opinion. From the tech center where I work, we are developing technologies to help the company meet these targets. The Repsol Technology Lab is the center where I work, and it's a different complex in the southern area of Madrid with avant-garde facilities. We have 20 specialized labs, 35 pilot plants, and currently we have more than 200 scientists from many nationalities, with an investment of about 64 million euros per year for research, and always with the support of the Entrepreneurs Fund and corporate venturing, which is venture capital of Repsol. And currently they're investing in 20 startups with disruptive technologies related to circular economy and the reduction of emissions. And we have another small department, which is open innovation, which helps us to really establish and get in contact and get in touch with different tech centers and university centers and universities to allow us to get to know what's being developed to support technologies that do have potential.
Right now, we are focusing on three main areas of research. Perhaps the strangest, or the one we are working on a lot, is related to asset optimization, computational chemistry, deep learning, robotics, nanotechnology, materials, digital characterization, quantum computing, things that you, well, might not have imagined initially. We have an advanced line related to mobility and renewables, and we're looking at renewable fuels there, optimization of energy consumption at domestic level and industrial level. We have batteries, lubricants, geothermal. But what I could perhaps highlight is all of the research that we're carrying out related to the circular economy and the reduction of carbon emissions. I would say that my team, where I am, we're in a deep tech platform. So we identify and validate the technologies which are emerging and are being developed in other places, so we can visualize the great opportunities for the energy sector. And this also allows our group of freaky people to think about core business, or not only core business, in fact, but to actually start to think about other businesses that would never have been considered in the past. So we have 4 main pillars and a cross-cutting or transversal line. And we're here talking about the biotechnology. So I'm going to talk very quickly about VFA because I think we all know what we're talking about when we are talking about volatile fatty acids. Here we have the structure in case anybody's forgotten. Here we're talking about short chain C2 to C6, and they can be linear or branched. Here we have the pillar for constructing a lot of chemicals that we might not even be able to imagine. And right now, practically all of the VFAs are obtained by means of thermochemical processes using the raw material oil, crude oil. This gives rise to primary VFAs, the pure VFAs. And it's very important to understand that if we use different raw materials, alternative raw materials, which we could have, well, we are able to obtain mixed VFAs or pure VFAs. And the pure ones can be done through purification with pure crops, but the performance when you use pure crops is quite a lot lower. But in a certain degree, we'd have to use all of the kinds of purification for these materials. And here we have some of the applications, the most noteworthy ones. In the case of acetic acid, for example, 50% of the market for acetic is in the production of vinyl acetate, which is used to obtain many products, for example, polymers. And also, the other 25% of the market is focused on obtaining, synthesizing terephthalic acid, which is fundamental for producing PET. It's one of the polymers that we have in our synthetic clothing, for example. And if we talk about propionic, that's used as in bread. It's a preservative to stop your loaf of bread going off. Butyric is used for biofuels, fragrances, cosmetics, chemicals. C5, above all, for pharmaceutical compounds, polymers, lubricants. It's even used for sedatives. And caproic acid is important for food, as a food additive, and it's used for the synthesis of additives for paint as well as antimicrobials. One thing we have to bear in mind is that the mixtures of VFAs can also be used. They are useful as such, and from my personal point of view, I think that it's fundamental to reduce the costly downstream processes, this possibility of using mixed VFAs. They're being, right now we have different lines under development, the production of PHAs, bioenergy, and sources of carbon in processes for the elimination of the nutrients, nitrogen and phosphorus. And right now, we have development in scientific centers. They serve as raw material in the process for producing PHAs. They can also help to produce microbial oils for biodiesel ingredients, and it helps in the process for hydrogen and methane because we use it in the process for biogas production and even for biobutane. And we have also the use of these compounds as a source of carbon for the elimination of nitrogen and phosphorus, which causes problems in the revalorization of effluents from water treatment. And so if we focus on butyric acid, here we can see a huge amount of chemical modifications of butyric acid to give rise to different esters, for example, for polymer synthesis, for perfumes, chemistry, medicine. But we wanted to look for a new application which hadn't been described or even visualized as yet. So what else can we do with butyric acid? What we did was to try to develop a process or methodology for converting these volatile fatty acids coming from a controlled process using alternative carbon sources from waste, which could give us this propylene molecule. Propylene is basic if we want to make polypropylene, which is what we have in our Tupperware boxes, for example. And according to the literature, we saw two routes. We had the chemical route and the biological route. I'm going to explain to you very briefly the results that we obtained. Without going into details, we evaluated the two lines, the chemical and the biological. We designed a whole system online in order to feed butyric acid into a system of zeolites, which we analyzed to see the production of propylene. We didn't use commercial zeolites, we used our own, and the results were very good, but the catalyst or the catalyzer died after about 11 minutes. And you had to use ultra pure butyric acid without any water. And if you bear in mind the origins of the VFAs that we were going to be using, it was very complicated. So we discarded that possibility. And in parallel, we were looking at the enzyme results, the biological side. And here we can see the different cultures. The one that has the enzyme, which is a redder color. We just have the examples here. And in this particular case, the enzymes showed that they had good activity for converting VFAs, which were longer chain VFAs. But if we look at the shorter ones, if we had short chain VFAs, the results were much worse. Around 1%, the conversion was very, very low. Nonetheless, we've seen a lot of potential in this line of research, and these results are from 2022, and we're continuing in 2023, trying to work with this line of research. We did a preliminary study looking at the figures to see whether they were profitable processes. And the problem we have right now is that the processes, biological processes, are very hard to sell compared to chemical processes. Right now, as things stand, no bonus is being paid for a product which comes from a renewable source. So it's hard to compete with established, efficient chemical processes. And the added problem here is that we have also a reduction of mass of 50% when we lose the CO2 from the acid group. So therefore, in order to get a ton of propylene, we have to have 2 tons of butyric acid. This means that the raw material cost is doubled. If I have to sell propylene at 1,300 euros, if the price on here isn't going to go down, I'm not going to be able to make a profit from that process. And that is the final thought. Right now, we have to, even in companies, we have to start to visualize biotechnological processes, which will be able to use alternative raw materials, even though we have to initially understand that it's very difficult right now, as things stand, for these processes to be economically competitive, but they will be in the future. That's what we hope.